when the signal is transmitted from transmitting antenna, it propagates through the medium and it is received at the receiving antenna. When this signal is propagating through any medium, the signal propagates from transmitting antenna to the receiving antenna in the form of electromagnetic wave. So for practical purposes, it is necessary that we should know the power relationships related to this electromagnetic wave. How much is the power transmitted? How much is the power received? How much is the attenuation taking place because of the attenuation characteristics of the propagating medium? So it is necessary to know all these things. So in this video, you are going to learn what are the power relationships related to the electromagnetic wave. So these power relationships we specify in terms of Poynting vector and Poynting theorem. So let us go ahead. Now, what exactly is a Poynting vector? Now we have a transmitting antenna here, and the signal is propagating from the transmitting antenna to the receiving antenna. Now during this process, the amount of energy flowing through per unit area perpendicular to the direction of the incident energy per unit time is called as Poynting vector. So this is what we mean by Poynting vector. Now mathematically, the Poynting vector is represented as the cross product between the electric field vector and the magnetic field vector. So it is P equal to E cross H, where E it is the electric field intensity, H it is the magnetic field intensity. Now we know both this E and H both are vector quantities. So that means the Poynting vector P, it is also a vector. Now the direction of P, it is perpendicular to both, that is E as well as H. For example, if electric field is oriented in X direction and the magnetic field is oriented in Y direction, then in that case the Poynting vector as per this equation, it is E cross H. So that means it will be perpendicular to both. So the direction of Poynting vector, it will be in the Z direction. So this means the electric field is oriented in X direction, magnetic field is oriented in Y direction, and the electromagnetic wave, it is propagating in Z direction. Now the Poynting vector is also called as the instantaneous energy flux density, represented in watt per meter square. Now let us see the corresponding equations for this. If we have some volume here, so as per Poynting theorem, the net power flowing out of this volume is equal to the time rate of decrease of stored electromagnetic energy in that volume decreased by conduction losses. Now let us represent this statement in the form of equation. So what this means is that the net power flowing out of a given volume, so that I write on the left hand side. So it is total power leaving the volume equal to time rate of decrease of stored electromagnetic energy. So inside this volume, the energy is stored in the form of electric field and magnetic field. So that is the rate of decrease of stored electromagnetic energy in that volume decreased by the conduction losses. So in this volume there may be some ohmic losses also. So the total power leaving the volume is the rate of decrease of stored electromagnetic energy minus ohmic power dissipated due to motion of charge. So this we represent in this diagram. So if the power entering inside some closed volume is power in, then some of this power it will be lost in the form of ohmic losses, whereas some power it will be stored in the form of electric energy, so that will be in the form of electric field. Some of the energy it will be stored as magnetic energy, that means in terms of magnetic fields, energy stored in the magnetic fields, and the remaining energy it will flow out of this volume, so that is power out. So this is the power flow if we consider some particular volume. So as a Poynting theorem, now we are going to find out the equations for all these terms. For a given power entering inside the volume, then how much is the power coming out of this volume, what are the ohmic losses, what are stored energy in electric field, what is the stored energy in magnetic field. So we are going to find out all these equations using this Poynting theorem. So this is what is Poynting theorem. Now all these equations, they will be in terms of the electric field vector and the magnetic field vector. Now before going to the derivation of Poynting theorem, first we will revise some concepts about the power density, the instantaneous power and the average power, some equations which are useful for while solving problems. Now as we have seen, if electric field is oriented in x direction and if the magnetic field is oriented in y direction, so H we assume it is oriented in y direction, this means electric field has only x component, so that is Ex Ax, whereas the magnetic field has only y component, so that is Hy Ay. Now as we have seen, Poynting vector is nothing but it is the cross product of E and H, so it will be oriented in z direction. So this is the Poynting vector P. Now as we have seen, this Poynting vector P is nothing but E cross H, which is oriented in z direction. Now we substitute E as Ex Ax and H as Hy Ay. This gives us Ex Hy. Ex is the magnitude of electric field, Hy is the magnitude of magnetic field intensity. So the product of these two, and the Ax cross Ay, that is Az. So this we can write as Pz Az, the power propagating in z direction. Now the electric field which propagates in space, it propagates in sinusoidal manner. So it can be represented as Em cos omega t minus beta z Ax, where Em it is the peak amplitude if it is varying sinusoidally, then Em it is the peak amplitude of this, t it is the time variable, omega it is the angular velocity, beta it is the phase constant. it represents how the wave changes phase, and the unit is radian per meter. And z, it is the distance as this wave propagates in space. So this is how we can represent electric field vector, E equal to Em cos omega t minus beta z, and this electric field vector is oriented in x direction. So that's why we use here unit vector ax, which gives direction to this. Now, in case of our conventional circuits, we know the ratio of voltage upon current, it is the impedance. In the same manner, for electric fields and magnetic fields, the ratio of the electric field to magnetic field, it is also impedance. It is represented as eta, so which is the impedance. So electric field corresponds to voltage, magnetic field it corresponds to current. So ratio of electric field to magnetic field, it is intrinsic impedance eta. The value of eta, it is different for different medium. So more details about this eta, propagation constant, intrinsic impedance, and so on, we'll study in the topic uniform plane wave propagation. That is the last topic in this subject. So eta, as we have seen, it is the ratio of electric field upon magnetic field. So Em upon Hm, that is the peak value of electric field divided by peak value of magnetic field. And eta 0, this represents the intrinsic impedance for free space. And this value is 120 pi or 377 ohms. Now, as we know, eta is E upon H, and earlier we have represented E in the form of a cosine wave, that is E equal to Em cos omega t minus beta z Ax. So similar to that, we can represent the magnetic field intensity, the equation for magnetic field intensity, which also varies sinusoidally. So it is H equal to Hm, that is the peak value of magnetic field intensity, cos omega t minus beta z Ay, because it is oriented in y direction. So as we have seen earlier, omega, it is the angular velocity, t is the time, and beta, it is the phase constant. Beta, it is the phase constant. Unit of phase constant is radian per meter, and z is the distance. Now, according to Poynting theorem, we have P is equal to E cross H. So substituting the equations for E and H, what we have written earlier. So this is Em cos omega t minus beta z Ax, and H we represent in terms of E. So H we can write as E upon eta. So the same equation for E, if we divide by eta 0, it becomes H. So this is expression for H. So this is E cross H. Now Ax cross Ay, it will be Az. Then Em into Em, it will be Em square, and cos into cos, it will be cos square. So this simplifies to Em square upon eta 0 cos square omega t minus beta z Az watt per meter square. So this gives us the power density measured in watt per meter square. So this is the instantaneous power density in watt per meter square. So if we multiply this expression by area, then it gives us net power density through particular given area. Now the average power density we can find out if we take average of the instantaneous power density over one period. So one period we consider as T. So taking average, that means integrating the instantaneous power density over a period of T, that means one cycle. So that period 0 to T, and dividing the time period, that is 1 upon T. So it is Em square upon eta 0 cos square omega t minus beta z dt. Now solving this gives us the average power density as 1 by 2 Em square upon eta 0 watt per meter square. So this is the expression for average power density, watt per meter square. So if we multiply this by given area, which is normal to the direction of power, then this gives us the average power flowing through a particular given area, which is normal to the direction of power flow, that is in watts. So these are the expressions for instantaneous power density and average power density. Now let us prove the Poynting theorem. Now we have seen the Poynting theorem, it gives us the power relationship. That means if we assume P in is the power entering inside this volume and power P out, it is the power leaving this given volume, then some part of this power, it is lost in terms of ohmic losses. Some part of this power, it is stored inside this volume in the form of electrical energy. It is stored in electric fields. Whereas some part of this power, it will be stored in the form of magnetic energy, which will be stored in the magnetic fields. Now, in many practical applications, it is necessary to find out all these powers. That means how much is the power entering inside this particular volume, how much is the power coming out of this volume, how much is the power lost in ohmic losses, how much is stored in the form of electrical energy, how much is stored in the form of magnetic energy. So all these relationships should be known in the form of equations. So that is what is Poynting theorem. So that we are going to find out now. Now let us start from the Maxwell's equations. Now we know the Maxwell's equations give us the relationships between electric fields and magnetic fields. So these Maxwell's equations are very useful to find out all the relationships in communication engineering, which are wherever the power flow is in the form of electric fields and magnetic fields. So let us start with this Maxwell equation, which we have written earlier for time varying field. So this is curl of H is equal to J plus dd by dt. So we have seen earlier this J, it is the conduction current density, and this dd by dt, this is the displacement current density. So this we have seen discussed in detail in some of the previous videos. So we'll start with this Maxwell equation. Now rearranging this equation, on the left hand side we write as J. So J equal to del cross H minus dd by dt. Now using the relationship D equal to epsilon E, we write this equation in the form of E, that is minus epsilon d by dt here. Now pre-dotting this equation, that means we take dot product of all these terms on both the sides by E. That is E dot J equal to E dot del cross H and so on. So we can write this in the form of equation 1 as E dot J equal to E dot del cross H minus E dot dd by dt equal to E dot del cross H minus epsilon E dot d by dt. So pre-dotting all the terms by E. Now we make use of this standard vector identity, that is divergence of cross product of E cross H, that is divergence of E cross H. So this is same as H dot del cross E minus E dot del cross H. So rearranging this equation, so this E dot del cross H we shift on the left hand side and the remaining terms on the right hand side. So this gives us E dot del cross H equal to H dot del cross E minus del dot E cross H. So here we interchange the dot operator and the del operator. Now substituting this equation number 2, so this we will substitute in this equation number 1 for E dot del cross H. So substituting equation 2 in equation 1. So this term will be substituting here. So rewriting this gives us E dot J equal to now H dot del cross E minus del dot E cross H minus epsilon E d by dt. Now using one of the Maxwell equation which we have written earlier, it is curl of E is equal to minus dB by dt. So by making use of this Maxwell equation, we substitute this del cross E as dB by dt here. Now for this B in this equation, we substitute B equal to mu H. So substituting B equal to mu H, that is the next step. So this gives us this here minus mu dH by dt. Now rearranging these terms, since mu is a constant, we can take outside of this bracket. So we can write it like this, minus mu H dot dH by dt. Now then this term minus epsilon E dot d by dt minus this term del dot E cross H. Now these terms H dot dH by dt and E dot d by dt will substitute it as 1 by 2 d dt H square, because 1 by 2 d dt H square, it is nothing but 1 by 2 2H d dt H. So if this 2 cancels, this is nothing but H dot H into dH by dt. So in the same manner, E dot d by dt we substitute as 1 by 2 d dt E square. So substituting this here in equation 3, this gives us E dot J equal to minus mu 1 by 2 d dt H square minus epsilon 1 by 2 d dt E square minus del dot E cross H. This is the same equation what we have seen in the previous slide. Now we just rearrange this. We shift this mu here, being constant, we can shift it anywhere. So minus d dt mu H square by 2. Similarly here we shift this epsilon here. So this is minus d dt epsilon E square minus del dot E cross H. This thing we can rearrange as minus d dt mu s square by 2 plus epsilon E square by 2 minus del dot E cross H. Now we have seen earlier, for the given volume we are interested in finding out what is the relationship between the power entering, power leaving out of this volume, and how much is the power stored inside this volume, how much is the power lost inside this volume in the form of ohmic losses. So we are interested in that. So for that purpose, taking integral of equation number 5 over the given volume, integrating both sides. So this is volume integral E dot j dv minus d dt volume integral, this term, mu square by 2 plus epsilon E square by 2 minus volume integral del dot E cross H dv. Now the last term here, del dot E cross H dv, will apply here divergence theorem, and the volume integral will convert into surface integral. So let us convert this last term using divergence theorem, the volume integral, to surface integral. So this becomes surface integral E cross H dot ds. Now rearranging this equation, shifting this last term on the left hand side and all other terms on the right hand side. So this gives us minus surface integral E cross H dot ds. This will shift on the left hand side. So the negative sign becomes positive here. So this is minus surface integral E cross H dot ds volume integral E dot j dv d dt volume integral mu square by 2 plus epsilon E by 2. Now we are almost reached to the end of this derivation. Now let us find out what are all these three terms in this equations. Now if you see the terms here, so the first term E cross H, we have seen earlier E cross H, it represents the power. The first term, it represents the power entering inside the volume, and that's why the negative sign. Now J, we know it is the current density. So the dot product of E and J, that represents the power lost in terms of ohmic losses. Now whereas this term here mu s square by 2, the first term represents energy stored in the form of magnetic field, in the form of magnetic energy. Whereas this term epsilon E square by 2, this represents the energy stored in the form of electric energy. So this equation is nothing but the final expression for Poynting theorem. So as we have seen, the first term integral, surface integral E cross H dot ds, it represents the ingoing power flux over the surface S. E dot j dv, it is the total dissipated power in volume at any instant due to ohmic losses. And these two terms here, the magnetic energy, first term represents the magnetic energy stored within the volume, and the second term, as we have discussed, it is the energy stored in the form of electrostatic energy stored within the volume. And both together it represents the rate of decrease due to total electromagnetic energy within the volume V. So this is what is Poynting theorem. Now let us go through the one example. Now here some equation is given for electric field. So EZT equal to 50 cos omega t minus beta z ax. So it is the electric field vector oriented in x direction which is given, and it is asked to find out the power flowing in the circular area of radius 2.5 meter. in the plane z equal to constant. So the expression for electric field is given, and we are asked to find out the power flowing in the circular area of radius 2.5 meter. So that means we have to determine here Pz. So first we'll find out the average power density, and then that will multiply by the surface area, we'll get the answer. Now E is given here, and we know the ratio of E upon H, it is eta. So based on that, we have seen earlier eta, that is the intrinsic impedance, that is nothing but E upon H. Now here E is given, so we can write now H in terms of E. So H, expression for H, now we can write as E upon eta. So this means this is nothing but eta we consider for free space. So for free space it is 120 pi. Now this becomes 50 cos omega t minus beta z divided by eta, which is 120 pi for free space. Now as per Poynting theorem, we know P is E cross H. So substituting E and H here, so this is 50 cos omega t minus beta z ax cross 50 cos omega t minus beta z ay divided by 120 pi. So this becomes 50 into 50 divided by 120 pi. If it is calculated, it comes out to be 6.5. So this is 6.5 cos square omega t minus beta z az. So this is the power in watt per meter square. Now the net power flow in z direction, it will be E0x, that is the peak value of electric field intensity square divided by eta. We have seen divided by twice eta. We have seen this expression earlier, into the area S. So substituting these values, peak value of electric field intensity is 50. So this is 50 square divided by 2 into 120 pi, that is eta, multiplied by area, that is pi r square. So pi, and the radius is given 2.5 meters. So multiplied by 2.5 square. So this comes out to be 65.1 watt. So this is the answer. The power which is flowing in a circular area of radius 2.5 meter in the plane z equal to constant. This is the final answer for this problem. So in this video we have seen what is a Poynting vector, what is the Poynting theorem, and what are the corresponding equations which represent the power entering inside the volume, the power losses taking place, energy stored inside the volume, all these equations are represented in terms of Poynting theorem.